sequences. So sequences naturally lay the groundwork for what's about to happen, namely a discussion of series. Okay? So let's finish talking about sequences. Now, what did we mean by a sequence being, okay, and first of all, let me just ask, what is a sequence? Like if you had to describe what a sequence is to a non-math person, what would you say? Okay, Jared, you had your hand up there. It's just an infinite, like it's an ordered list of numbers. Yes, like it's an ordered infinite list of numbers. And by the way, some of those numbers might get repeated lots of times. Yeah, maybe the entire list is just the same number over and over and over again. Okay, so we messed around with sequences, like A1 is the first term in the sequence, A2 is the second term in the sequence, etc. By the way, you don't have to use A sub whatever. You could use B sub whatever or X sub whatever, right? There are alternative notations for sequences, but we use this curly brace notation a lot of times to help us understand that we're talking about a sequence of numbers, okay? So AN, the sequence AN is monotonic if its terms are non-decreasing or non-increasing. That's sort of an awkward way to say that, okay, so non-decreasing, what am I talking about? What is it never allowed to do? Go down, strictly down, okay? So it could stay the same, or it could go up at times, or stay the same for a while. That's what non-decreasing means. Non-increasing is just the opposite of that, okay? So it never goes up. It always is either staying the same or going down, okay? That's what monotonic means. We talked about what it means to be bounded above. It means that there's a ceiling to all the terms, like that the terms are always trapped below some kind of ceiling. Bounded below, you're talking about a floor. There's like a floor. There's a number that all of the terms in the sequence live above. Okay? And you say that a sequence is flat out bounded if it is bounded above and below. The end, right? Okay? So I wanted to spend some time talking about the boundedness and monotonicity. That sounds very, complicated, but I want to talk about the boundedness and monotonicity of each of the following sequences. Now, you might say, how can I tell if a sequence is monotonic, right? Well, a sequence is monotonic if it's always moving in the same direction, correct? And we actually have a tool from calculus that tells us if a function is moving in the same direction. And it's the derivative, yes? How could you tell if a sequence is tending to move in an upward direction? The derivative would be positive, right? And that would tell us that we have an increasing sequence. If, on the other hand, the derivative is negative, then you're tending to trend in a downward direction. It's a decreasing sequence. And again, you could use terms like decreasing if it's always going down, or increasing if it's always going up. Otherwise, you have to use these unfortunate terms like non-decreasing and non-increasing. Okay, so let's talk about the boundedness and monotonicity of these guys here, okay? So let's see. What is going on here? My pen is having some issues. This thing, there we go. What in the world? Hang on a sec, guys. Give me a second. All right, the pencil is now working. Okay, so here we go. An equal to 4n over n plus 1. Okay, what about the boundedness? Is this thing bounded? What about a lower bound? I mean, what's true? No matter what value of n I plug in, can you think of a number that it's always above? Yeah, an is greater than or equal to 0, and I'll even use this weird notation for all n, okay? Number 4, all in. What about something that this is always less than or equal to? An is less than or equal to, okay, so I think it's equal to 4n over n plus 1. Well, watch this. What if I added 4 to the numerator and just left the denominator alone? Do you believe me that that quantity is bigger than the thing I started with? What's the only thing I did? Added 4 to the numerator, which clearly increases it. What would motivate me to do that? Well, what's this? What's 4 times the 4n plus 4? I can factor out 4, right? So this would be 4 times the quantity n plus 1 over n plus 1. And hello, that's just 4. So an is always bigger than or equal to 0 for all n, and an is always equal to or less than 4 for all n. Right? So what can we conclude about an, about the sequence an? So the sequence an is what? Bounded. Okay, that's my shorthand way of writing bounded. Okay, so that thing is bounded. Sometimes you have to do some weird stuff like that. You know, just try to get stuff to go away and whatnot. And in this case, I had to add 4 to the numerator and stuff canceled. Okay, so this thing is always trapped between 0 and 4. Yeah. Well, why not? Well, why not? I mean, look, I'm not claiming that an is equal to that, right? I mean, I'm not saying that an is equal to that. So I'm just saying, look, I'm trying to find a number that this is always below. And I just realized if I add 4 to this, the n plus 1s are going to cancel. I'm not changing the formula, right? An is still equal to what? 4n over n plus 1. And all I'm saying is, what do I have to do to get rid of this dependence upon n? Adding 4 would be a good idea. And that would only increase the value, yes? Does that make sense? It's a little bit, sometimes you just have to resort to a little bit of trickery, unfortunately. Okay, it's bounded. Yeah.
Can you explain how you got that an is always greater than 0?
Well, just think about it. If I plug in, I mean, remember what's n? In what values of n am I plugging in here? Yeah, right? You're only plugging in 1, 2, 3, 4, etc. Right, so you're only plugging in the counting numbers, the natural numbers. Remember that? Okay, so it's pretty clear that all of those are bigger than or equal to 0. Okay, no matter what I plug in. Make sense? Our sequence is always trapped between 0 and 4, so it's bounded. Okay, what about monotonicity? Okay, so monotone. Is this thing monotone? Well, to figure that out, what do you think I'm going to do? Take the derivative, okay? So I'm going to take 4n over n plus 1 and take the derivative. And I'm taking the derivative with respect to n, which is a little weird, yeah? But that's the variable after all. So I use the quotient rule, right? It's going to be low times the derivative of the high minus high, which is 4n. What's the derivative of the low? 1 over the denominator squared. Yeah? Okay. So look, if I were to distribute this 4, what's going to cancel? Yeah, 4n just cancels. And I'm left with, interestingly, 4 over n plus 1 squared. And what do you notice about that all the time? No matter what n value I plug in, that's always positive. So what can we conclude here? Thus, the sequence an is monotone, right? But we can say more than that. We actually know which direction it's moving always. Which way is it always moving? So it is increasing. Okay, is increasing. Okay, so let's just think about this for a second. What did we say that this sequence is trapped between all the time? 0 and 4, and it's always moving in an upward direction, correct? Okay, so like let me just kind of draw a little picture on here just for us to kind of think about. Okay, so here's the y-axis right here. Okay, here's the y-axis. Okay, here's the x-axis. Okay. Okay, and basically I'm gonna draw another horizontal line at y equal to 4. So what this says is, first of all, if I plug in n equal to 1, okay, I get 4 over 2, yes? Which is 2. Okay, so that's the value of that, right? So this is the value of A1. Okay, so A1 equals 2. Does that make sense? And then what happens? And by the way, we know that this thing is going to increase with n. We just figured that out, right? What happens if I plug in 2? 8 over 3, right? 8 over 3, which is like right here. If I plug in 3, what do I get? 12 over 4, which is 3, which is slightly bigger, yeah? 3 is slightly bigger than 8/3, yes? 8/3 is like 2 2/3. And then 4, I'm telling you, it's just gonna keep going up. Does that make sense? See what's happening here? If I kept going, I would continue to get closer and closer, or I would continue to kind of move in this upward trajectory of a direction, yeah? Because this thing is moving up, and is trapped by a ceiling, what do you think that's going to force this sequence to do? It's going to converge, yes? And that's what this theorem says right here. This is called the monotone convergence theorem. This is known as the monotone convergence theorem. It says if you have a bounded sequence that is monotone, then the sequence converges. Yes? Okay? Doesn't that make sense? If it's trapped and it's only moving in one direction, it has to converge eventually, yes? Because it's either going to be moving in an upward direction towards a ceiling, and the ceiling will sort of trap it and force it to get closer and closer and closer to some number as we go out further in the sequence, or it will be moving in a downward direction, and there will be a floor that forces the terms to get closer and closer and closer to some number as we go further out in the sequence. Does that make sense? In fact, you can actually say something stronger than this, or actually you could say something that's a little bit more specific than this. What do you think we could say? Do we actually need the sequence to be bounded? What could we say? I mean, what could we say instead? Yeah, in the direction it's moving. If it's bounded in the direction that it moves, then the sequence converges. So for instance, if the sequence is increasing and bounded on which side? Above, the sequence necessarily converges, yes? If the sequence is decreasing and is bounded below, the sequence necessarily converges. Do you see what I'm saying here? Okay? All right. Hopefully that kind of makes sense. So let's discuss some of these other ones. What about n e to the minus n? What about this guy right here? N e to the minus n over 2. Okay? First of all, what is it? Look, we'll talk about boundedness. We'll talk about boundedness later. Let's first talk about monotonicity. What do I have to do to determine monotonicity of this thing? Take the derivative. So that means I need to go n e to the minus n over 2 derivative. Okay. I'm going to have to use the product rule, correct? So it's going to be the derivative of the first times the second, e to the minus n over 2, plus the first times the derivative of the second. What's the derivative of the second? Huh? Negative 1/2. Negative 1/2 e to the minus n over 2. And what could I factor out of this, just so I can get my mind around what's going on here? What could I factor out? E to the negative n over 2. Does that contribute to the sign of the derivative? Not really. That's always positive, correct? E to the anything is always positive. So if I pull that out, what's left behind here is 1 minus n over 2. Okay? Okay. So what do you think you can say about this thing, this little product? The first thing's always positive. What about the second thing? Yeah.
Would it be like, would it be positive until a certain point and then it will go?
Yeah, it's negative after a certain point because n is going to overwhelm that 1 pretty quickly. In fact, it's going to be negative after n equal to 2, right? So, I mean, you can go over here to the side and you can play with this and say, okay, when is, I know it's eventually negative. 1 minus n over 2, this is negative. When? We'll just kind of add this over there. So that's when 1 is less than n over 2, which, you know, and then I multiply through by 2, which happens if n is bigger than what? 2. So for n equal to 3 onward, this thing is negative, right? All of these go back and forth. So this guy is equivalent to n being bigger than 2. So in other words, this thing is less than 0 for all n. I'm writing for all. I'm using that upside down a thing. For all n bigger than 2, which I'll say bigger than or equal to 3. So that means that this thing is eventually decreasing. So like at first it might kind of jump up a couple steps, but then what happens after that? It starts going down from that point on, okay? So let's just say in this case, the sequence an that we're dealing with here, n e to the minus n over 2, is eventually, let's just say eventually, and we can even say very specifically when it starts. Eventually what? Decreasing. Okay, it's eventually decreasing. Does it converge? It's decreasing. In order for it to guarantee convergence, I would need to think of something that is a bound from which side? Below. Is there an obvious bound for this thing from below? Because usually we're like, oh man, you know, I need to find bounds on both sides. But if you know that the thing is moving in one direction, that's not necessary. Do you know what I'm saying? Is there an obvious thing that this thing is always equal to or greater than? How about 0? Yeah? So just note the following. Note n e to the minus n over 2 is greater than or equal to 0 for all n, right? That's always equal to or greater than 0. So these two facts combined, like this one right here and this one right here, what do I know is true about the sequence an? It has to do what? It has to converge, right? So these two things tell us that sequence an converges.
So how is n e to the negative n over 2 always greater than or equal to 0, but then it's negative 1?
Once again, what are the only n values that we're concerned with? What is n?
So it starts at 0.
No, 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 it starts at 1. Remember, n is always a natural number, yes? Okay, so don't plug in negative numbers or 0, yeah? It's like n equal to 1, 2, etc. Okay? So these things could, both of these first two things converge. Okay? By the way, let me just ask you, you know, we said that this thing was decreasing. This thing was decreasing if n was 3 or more, correct? So where does this thing reach its maximum value? Where does it reach its maximum value? By the way, you know this from Calc 1. Where does it reach its maximum value? When the derivative is 0. And where does that happen? So this thing right here is maximized, is maximized at n equal to, think about it, when is this, the derivative, going to be equal to 0? At n equal to 2. So the maximum value is what? Max at n equal to 2. So if I plug in n equal to 2, it's like 2e to the what? E to the negative 1. If I plug in n equal to 2, do you see that? So this right here is actually an upper bound, if you really wanted one. This is an upper bound. Because remember all that stuff we did with like finding maxes and mins? What we just saw is that the derivative was positive until I got to 2, and then it was negative after that. So where am I at? If it's positive before that and negative after, I'm at a maximum. What test was that called? Remember? You guys thought you could just forget all of that stuff, right? That's the first derivative test, yes? The sign of the derivative was positive before 2 and then negative after that. Therefore, this is a maximum. So if I really wanted an upper bound, I could write it down. Yeah, it's like 2 over e in this case, okay? But I don't really need that to guarantee convergence. The lower bound is all I needed because the thing's decreasing. Yes, Daniel. Okay. Sorry, it's all right. Yeah.
So I'm just making sure I'm understanding this correctly. So if it's increasing the upper bound for it to be
To converge.
and if it's decreasing the lower bound.
Yeah, you need the sequence to decrease and have a lower bound for it to converge. Yes. Yes.
So the upper bound can equal the max. So like the max can touch the upper bound.
Sure.
Okay. So it's not like an asymptote.
Right, because you see, I mean, it says less than or equal to be bounded above, right? It's allowed to be equal to the upper bound. Yeah. By the way, 2 over e, that's like less than 1, right? Isn't it? Because e is like 2.7 something, yeah? 2 over e is less than 1. So I could have used 1 as my upper bound. I could have said that this sequence is always trapped between 0 and 1. Because I know the maximum value for the sequence is 2 over e, which happens at n equal to 2. Yeah? Okay, yes.
So the bounds don't have to be like super close to the last, like the highest part it gets to, like you could have set down like the upper bound 3 to 4.
Yeah, that's right. I could say that, okay, look, an upper bound for this sequence is 38 trillion, right? Because clearly 2 over e is a maximum and 38 trillion is way bigger than that. Okay, so I mean, once you have one upper bound, you have an infinitude of upper bounds to choose from. Okay, and an obvious lower bound in this case happens to be 0. Make sense? Okay. By the way, what do these things converge to? Let's just quickly kind of think this through. What do these things converge to? As n goes to infinity, think carefully about 4n over n plus 1. What does that converge to? We know it converges. We know it's increasing and bounded above by 4. And what does it actually converge to? 4. Okay? You could use L'Hopital's rule if you wanted to, or you could just think about rational functions. What about this thing? So let's think about this for a minute. This is the same thing as n over e to the n over 2. Do you know what I'm saying? Yeah? And remember our little rule about growth rates? Yeah? What we had logarithm at the bottom of the hierarchy. We had polynomials next. We have exponentials, and we have factorial growth that whips all those things, right? So, okay, what's going to win? Both of these things go to infinity, but what's going to win? The exponential is going to just destroy the polynomial, yes? So what is this going to go to as n goes to infinity? That's going to go to 0. Yeah, you could use L'Hopital's rule to discern that if you wanted to, but yeah. Okay, what about these last two guys? The minus 2/3 to the n. What about minus 2/3 to the n? What do you guys think about that? What do you guys think? That thing's going to hop back and forth between negatives and positives. Does that make sense? So like, if I were to write things down, you know, like, so I would be negative 2/3. The next one is 4/9. The next one is negative 8/27. The next one is 16/81, etc. Can you think of two numbers that trap this thing the entire time? One, a -1 would work, because actually this thing is getting smaller and smaller the further I go out. Like in absolute value, it's getting smaller and smaller. Does that make sense? Yeah? So this thing is bounded, right? So it's bounded between -1 and 1. Yeah, so it's bounded. But does it, I mean, careful, is it monotonic? No, it is not monotone. So can I invoke the monotone convergence theorem here to guarantee convergence? No, we cannot. But does this thing actually converge? Does it go somewhere as n goes to infinity? Where does it go? 0. It actually goes to 0. Okay? By the way, this little sentence down here, I said, of course, like you can't really see it because it's covered up a little bit, but it says, of course, the converse is false. So like if you have a sequence that converges, that converges, that does not necessarily mean that it has to be bounded and monotonic. And it actually will end up being bounded, but not necessarily monotonic. This is an example where I have a converging sequence, but is it monotonic? No. Just because a sequence converges doesn't mean it has to be monotonic. It turns out it will be bounded though, because the terms have to get close to some number eventually. And so all the junk that happens at the beginning, you only have to worry about the first part of the sequence, and that stuff will be bounded. Okay? Okay? Okay, any questions on that? Okay, what about this last sequence, 3/2 to the n? Let's see, it's going to be 3/2, and then 9/4, and then 27/8, and then 81/16. Oh man, what is happening to this thing? It's increasing. By the way, you could figure out whether this is increasing or not by taking the derivative, yeah? So if I take 3/2 to the n and I take the derivative, how do I take the derivative of this? Do you remember? What's that? Say again.
It's like a to the n over
Times the logarithm of the base. This is an exponential. It's not n to the 3/2. It's 3/2 to the n. Yes, it's an exponential. It's itself 3/2 to the n times the logarithm of the base. Now, the logarithm of 3/2, is that positive or negative? Is the logarithm of 3/2 positive or negative? Yeah, that's positive, right? The logarithm is positive for things that I plug in that are to the right of 1. And this guy right here is also positive. Therefore, this whole thing is always positive. Therefore, this is what kind of a sequence? This is an increasing sequence. It's increasing, but is it bounded? No, this thing is unbounded. Okay? In fact, what does this thing go to as n goes to infinity? Clearly, it goes to infinity. Okay? It just grows without any kind of any kind of bound whatsoever. Okay? Questions? Any questions? Okay. Are you guys ready? It's about to get real. Here we go. Okay. This is where it starts to get kind of fun. And I'm serious about that. So here's the first question I want to deal with, and I want to think about this carefully together. Series is a different term from sequence, okay? That's the first thing I want to point out. We've been talking about sequences, which is an ordered list of numbers, yes? An infinite ordered list of numbers. A series is an infinite sum. And by that I mean like it's a sum of an infinite number of terms. Does that make sense? Now, you might say to yourself, how could you ever add an infinite number of terms together and get something finite? Well, I think you actually have done that sort of thing before. So if I take, for instance, 0.3 plus 0.03 plus 0.003 plus 0.0003, etc. So what am I going to get? Yeah, this is 0.3333 repeating. And you guys all know that that's a third. Yeah? Didn't you know that? So there you can see that something mysterious is going on, where it is possible to add up an infinite number of things and end up with something finite. Okay? Now what about 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd, etc.? Well, let's think about that for a minute, okay? So I want to go up here. Watch, here's 0, and here is 1. And here is, actually, I'm going to go all the way out to 2. Okay? So think about it. 1. Okay, so I start with 1. Okay, and then what does it say to do next? Add a half. Okay, which gets me to like right here. So that's what I have so far, 1.5, yes? And then I add a fourth. What's that? That's half of what's left. So that gets me to right here. Okay, what about an eighth? That's half of what's left. Okay, what about a 16th? That's half of what's left. See what's happening here? We just keep taking half of what's left. What do you think that this thing is going to add up to in the end? 2. Okay? But we would rather not have to resort to such cleverness in general. You know what I'm saying? We want to have some kind of discernible way to deal with these things without having to like draw pictures and remember things from elementary school about repeated fractions or something like that. Yes, there's got to be some kind of systematic approach to doing this. Yes, Marie. It won't ever reach it, but it will reach it in the limit. It's kind of like, a sequence. That's why we just did sequences. It's kind of like how a sequence never actually reaches, like that one we did up there, 4n over n plus 1. That never actually reaches 4, but it gets arbitrarily close to 4 the further out we go. Does that make sense? So it kind of reaches it in the limit, if you will. And the same thing is true here. The more terms we add, the closer we get to what? 2. So you specify how close you want me to get to 2. I can do it by adding enough terms together. Does that make sense? Okay. All right. let's define a series, and we'll talk about what it means for a series to converge. And this is going to be our personal obsession for the next couple of weeks, trying to understand when a series converges and when it does converge, what it converges to, okay? Notice I'm saying series converge, not sequence necessarily, although we're going to have a sequence that is connected to every series that we're going to be obsessed with, okay? All right, so let's define what a series is. A series, and incidentally, look, do you guys remember summation notation? Okay, so you have sum n going from 1 to infinity, a sub n. What that means is like a1 plus a2 plus etc. That means you're just adding all these things together. That's called an infinite series. And a sub n is called the nth term, not of the sequence. It's the nth term of the series, right? And by the way, you could sometimes you even, instead of nth term, you often say it's the nth summand. Okay? Summand is also a legitimate thing to say. So this guy right here is the nth term or summand. Okay? And look at this, the nth partial sum. So the nth partial sum means that you simply add together the first n terms, right? So what I'm saying is this is like a1 plus a2 plus a3. And where do I stop this madness? an. Yeah, I kind of stop at some finite moment. Does that make sense? Okay. So like, and I use this notation right here, s sub n. So like, what would s sub 5 be? What would that mean? That would be the fifth partial sum. And what would that mean? What am I talking about if I say s sub 5? a1 plus a2 plus a3 plus a4 plus a5. Okay? What's s sub 1? What's s sub 1? a1. What's s sub 2? a1 plus a2. Okay? First partial sum, second partial sum, etc. Now let me ask you a question. So all the s sub n's are is that you're just adding together the first n of them. Like s sub 37 trillion is saying add together the first 37 trillion terms. Yeah? What do you think should happen if my sum is going to be something finite? My infinite series is going to add to something finite. What should happen as I add stuff on? Like s, what should happen to that sequence of partial sums? It should be getting closer and closer and closer to some number. Does that make sense? So to say that a series converges means that the partial sums converge to some number. Does that make sense? The partial sums, which is a sequence of numbers, by the way, because you have like S1, S2, S3, S4, and you guys all understand what I mean by these, right? S1 is A1. What's S2? A1 plus A2. S3? A1 plus A2 plus A3. S4? A1 plus A2 plus A3 plus A4, et cetera, et cetera. So convergence of the series means that the sequence of partial sums converges. That's probably the most important sentence that I'll say about series. Convergence of the series. Look, if you haven't heard a single thing that I've said the entire semester, hear this. Convergence of the series means convergence of the sequence of what? Partial sums. Okay? That's kind of like Genesis 1:1 of, of series convergence. Everything about series is tied up in the sequence of partial sums. I can completely determine what's happening with a series by looking at the sequence of partial sums. Okay, so once again, to figure out what's happening with a series, what do I look at instead? The sequence of partial sums. And if I can make sense of what's happening with the sequence of partial sums, I will in turn have figured out what's happening with the series itself. Yes.
To get like a, so we're talking about bound to see if it converge. Is there like a certain, so they would have to get smaller, right? As
That's something we're going to talk about. So we just talked about boundedness and monotonicity. If my sequence of partial sums keep adding a positive number each time, what's automatically going to be true about the sequence of partial sums? Which direction are they going to be going? Up the whole time. So if I can show that the sequence of partial sums is bounded, what is that going to tell you about the sequence of partial sums? It will converge, and therefore the infinite series will converge. Does that make sense? Well, I mean, it just depends on what you're adding together. It really just depends. Yeah. Okay, so once again, convergence of the series is determined by convergence of the sequence of partial sums. Partial sums. Okay? Let's kind of scroll down and digest that for a minute. So the sum of the series is the limit as n goes to infinity of Sn, if it exists. And by the way, I mean, that makes complete sense because the limit of as n goes to infinity of this, that's just the limit as n goes to infinity of a1 plus a2 plus dot 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 plus an, right? Because after all, what is this? Is that not just Sn? You know what I'm saying? Yeah? Doesn't it make perfect sense that I would tie up whether or not this series converges with looking at it, like looking at the first 50 terms, 51 terms, 52 terms added together, and kind of think about what's happening with that? Yeah? And as Daniel said, and this is actually going to be something that we're going to make rigorous later on. What has to be happening to the terms eventually as I add them on? Like if what would have to be happening in order for the partial sums to be getting closer and closer to some number? What would have to be happening to the terms? They would need to be getting smaller and smaller and smaller. It needs to not be affecting the overall sum that much. So that's going to be something that we're going to be able to use to our advantage later on, I promise. Okay? So convergence of the series, okay? So convergence of the series n going from 1 to infinity an means convergence of what? Convergence of Sn, where what is Sn? Sn is just a1 plus a2 plus dot 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 plus an. Okay? Okay? These things are one and the same. Convergence of that series means convergence of that. And this thing is equal to the limit as n goes to infinity of Sn, right? I mean, that makes sense, doesn't it? Because limit as n goes to infinity, that just means I've added all the terms together, basically, yes? It's the limit as n goes to infinity of the sequence of partial sums. Okay, the sum of the series is the limit of the sequence of partial sums if that limit exists. In this case, we say the sum does what? Converges. And it converges to the limit of the sequence of partial sums. If the limit doesn't exist, what do we say about the series? It diverges. Yeah? So if that thing doesn't converge, we say that the series diverges. Okay? And this is a key sentence right here, okay? I kind of put this down right here, okay? So let's kind of think about what this thing says. You will avoid a lot of confusion for yourself if you remember that every series has two sequences associated to it. namely the sequence of terms. Those are the individual summands, yes? You have the sequence of terms, but you also have the sequence of what? Right, the sequence of partial sums, right? And by the way, this thing, you know, can be rewritten as A1 plus A2 plus dot, 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 plus AN, right? So it's a different sequence where you've kind of added together the first n terms of the other sequence, yeah? So there are two things going on. You have the terms themselves, but then you also have the sequence of partial sums arising from them. You have to keep this straight. Am I talking about the terms, or am I talking about the sequence of partial sums itself? If you can't keep that straight, it is not going to end well, okay? You have to be able to discern between the actual terms and the actual partial sums themselves. That is very important. Yes, sir.
Don't those technically like equal each other?
What equal each other?
Well, because you said in like number 3 that A of n is the limit of n.
No, this limit is not the same thing as the limit as n goes to infinity of an. Here I am looking at the limit of the sums of all the terms added together up to that nth term. This limit, I'm just looking at the nth term only. Does that make sense? That's a big difference. Please keep these things like separated out in your mind. And again, I'm sort of being dramatic here, but I have seen mathematical corpses strewn all over the calculus landscape. And it all comes down to this issue right here. Keeping the terms and the sequence of partial sums clear in your mind, okay? Keeping both of those things clear in your mind. What am I talking about right now? Am I talking about the individual summands, the terms, or am I talking about the sequence of partial sums? Yeah? If you just keep those two things straight in your mind, you will save yourself a ton of trouble. All right? That's our little introduction to series. We'll start seeing how this stuff works next time.